Lawrence, you want to introduce yourself?
Yeah, sure. I'm a tech lead for GoPro. So how many of you guys know GoPro Plus? Oh, wow. Jeez. Give you a little background, like the GoPro platform, cover kind of like how our system work, what's GoPro Plus. Then we're going to continue on kind of like why do we choose ECS, you know? What was before ECS? And what were options besides ECS? Then the migration process. Here we kind of go to nitty-gritty stuff. You know, look more important stuff, the stuff you probably care, like how the heck we did that. Like we're gonna talk about a little IAM rows, TERRAFORMs, gonna throw some buzzwords, orchestration. Pretty cool, huh? And next, finally, lessons learned. What the heck did we learn? Yeah, we make mistakes. We all make mistakes. But part of being a software developer is kind of learning from your mistakes and improving, and you guys can learn from ours so you don't repeat our mistakes.
So as we mentioned, GoPro Plus is one of the main services we run on our cloud platform. It was launched in 2016. It's a subscription service that makes it easy to automatically upload, share, and edit your videos. You can do that from your mobile device. You can do that straight from the new GoPro cameras like the Hero 5. And you can share it with all of your friends, of course. So to make this possible, we particularly needed a scalable and cost-efficient solution. GoPro has a lot of very enthusiastic customers around the world, and they have a lot of video content, a lot of photo content that they want to upload and share. Let's talk a little bit about some of the platform components. So the AWS platform runs more than just GoPro Plus. It also does these things. So media upload, as we saw, photo and video processing, as you would expect. Also user subscription, management of users, etc. We also do device management. So GoPro Plus, the GoPro platform rather, also manages our devices out in the field, like the Hero 5 cameras, and like the drones, and like the mobile apps that run our software. So all of this is coming into our cloud platform, consuming our APIs, and in some cases, using the web front ends that we have. So today, our ECS cluster has around 40 services running on it in production. We process hundreds of thousands of API requests per minute, sometimes 500,000 per minute at peak. And right now, we've migrated all of our workers over to ECS, and we're in the process of migrating all of our web services. We're thinking that we'll have all of our web services running on ECS by the end of the year.
We're basically a bunch of microservices. And not only that, we have a bunch of clients. And these clients all talk to our microservices, and these microservices are both synchronous and asynchronous. And one thing I want to kind of show you is a little flow, like how kind of like an asynchronous portion part work. And this is where ECS kind of may fit in. Pretty much our clients and apps kind of talk to our web service, and they're asking for some work done. And we kind of track it, and it gets queued by these asynchronous workers. They could be doing something complex like processing media, or doing orchestrating some accounts for our users. After it's finally done, then it talks back to our web service saying, I am done. And then our clients will be constantly checking back to web service, is it done? And then once it's done, then it knows that the work is ready, or it could access the media or stuff. Let's go to the next part. The next section is we're talking about why do we choose, ECS? And that comes to my part here. Before ECS, we were using a third-party solution to do, all that complex stuff I show you, like that asynchronous event-driven system, where the worker's doing all this stuff in the background. I mean, developers needed like a simple self-serve service, but there was drawbacks. It didn't really give us transparency. We couldn't control the scalability, and then it was like too much abstraction to debug our problems. And then also orchestrations. There was a lot of orchestration issues. It wasn't quite perfect what we needed. And then monitoring alert, they didn't have that for us. We had to build our own solution. We ended up building some CloudWatch thing to support this.
There's a few details there we might go into. So especially around scaling up when we're using this third-party worker orchestration platform. Their scaling algorithm was basically a black box. It was something they provided as a service. We didn't get much control over that. So that was a problem for us. We didn't always know how much we were scaling or how much compute we were using. also, before we moved to ECS, we ran our own apps and microservices on our own AWS platform. But we did it a little bit differently. We did it in a pretty naive way. So although we were using Docker, we were running basically one Docker app container per instance. This is how a lot of you might start out if you're not using an orchestration engine. And it works. It makes sense in a certain kind of way. But it obviously wasn't as efficient as using something like ECS where you can pack all of the containers onto each instance. Also, we were using this time-tested model of rolling AMI images and then creating auto-scaling groups from the AMI images. So that's a pattern that I'm sure a lot of the audience is familiar with. We did that for a very long time. So that's simple because you're creating an AMI image at deploy time. You're creating the entire image, and then you know that that's going to become your next auto-scaling group. So it's predictable in that sense. It's also very inefficient because building an image might be rather large. It takes a long time to actually create the AMI. And for us, we were spending 30, sometimes 45 minutes on a deploy of a single microservice. So we had long and error-prone deployments. So that was where we were at before we decided to move over to ECS. And in order to get there, we did an evaluation process of these two familiar products. We looked at Kubernetes, and our engineering teams and DevOps teams spent quite a while evaluating both Kubernetes and ECS. We did a proof of concept with each, and we had a long list of maybe 50 criteria that we needed for our platform. We found that essentially both of these solutions offered almost everything that we needed. A lot of people really liked Kubernetes. We liked Kubernetes a lot. But we found that there were a few key items that ECS really did that Kubernetes wasn't going to do for us. So specifically, IAM roles specific to each service, that was really important to us. We wanted to be able to isolate the security of each service from other services running in the cluster because we have a lot of different databases. We have a lot of S3 buckets, SQS queues, et cetera. So at least at the time when we evaluated Kubernetes, there wasn't a good way to do that. I think there was a third-party way to kind of bolt it on. It didn't seem very stable, and we didn't really trust it with the security of these services. Second major point, of course, is that we were really familiar with AWS platform already. Our DevOps team has been running in AWS for a few years now, so very familiar with auto-scaling groups, CloudWatch, use it on a daily basis. So ECS for us, easy, one more level of abstraction on top of the services that we all know and love. Another big one for us was enterprise support. So we have enterprise support with AWS. We love those guys. They're awesome. We work with them on a weekly basis. And moving our entire production stack to a new container orchestration platform felt really important, especially to the business, to have enterprise support available. And it's definitely come in handy. We've talked to the product team at ECS on numerous occasions. They've made themselves very available to us. So that's been a really good thing. And then finally, very much of importance to the ops guys, there's no real cluster maintenance with ECS. So maybe what you're doing is you're updating your AMI image that's running in your cluster. That's as simple as editing the launch configuration. There's not much else you have to do. So I just wanted to kind of lay the land for the migration. So at GoPro, we have quite a few different development teams working in different locations. And even among our engineering teams locally, there's 5 or 6 of them, I think, that all had workers that were running in AWS that we needed to port over to ECS. For example, Lawrence's team is focused on media ingestion and processing and media metadata processing. So in our move to ECS, we decided to first migrate all of the workers before any of the web services. So these are just these asynchronous workers that place jobs on a queue, and other workers pick up jobs from the queue, as Lawrence showed. And so that's where we started. One of the things we were able to get out of this deal is infrastructure as code. We went with Terraform. We had some guys on the team that were familiar with Terraform, so we used that. And we terraformed almost everything, starting with VPCs, clusters, SQS queues, the task definitions themselves, and the Docker image tag that's baked into the service or task definition, the resource reservations for each service in ECS, IAM roles, environment variables, et cetera. So all of this we encoded in Terraform. This, for us, was a huge improvement to the previous way of doing things, which was no code at all, and just people would spin up these EC2 instances and hack on them and change things, and it wasn't always easy to tell what had been changed. In fact, we had no idea.
It gives us more transparency, definitely.
Yeah, so we decided to check in the Terraform code for each of our different parts of the stack with the service itself. So the DevOps team for us developed the base modules in Terraform. Then the development teams for each service imported those base modules and basically just edited them a little bit, but mostly just filled in the variables that they needed to do to get their service stack up and running. So those are just the obvious kinds of variables like the name, task definition, importantly, the resource allocation for each task. So moving to ECS, our development teams didn't really know how much CPU or memory their services would consume because they didn't really care because we would over-provision all of our capacity in EC2. Moving to ECS actually made us measure all of these things because you have to provide that minimum or maximum threshold. So that was something we sort of did for the first time. Ultimately, that led to a much more efficient use of compute because we're only allocating what we actually need. And then the last bullet point here is just about the CloudWatch alarms on SQS queues. So we scale our workers based on the length of the queue. So if there's more items in the queue, then we boot up more containers to run the workers. Another big part of this, as I mentioned, was VPCs. So we introduced new VPCs for every environment when we went to ECS. Just made it really easy to segregate our QA, staging, and production environments. And we terraformed all of that, like I said. And we also moved over to the new application load balancers. They were new at the time. So just a couple of easy wins that we kind of got for this migration. I think it's always a good practice to kind of look at the whole environment when you're going to migrate to something like a new platform.
Let's talk about kind of like the developer side of this migration. Porting code, it's just to give you a little context, like I showed you earlier that we process a lot of this media, and this media takes time to process. As a result is we have these long running workers that's doing all these tasks, and it takes time to launch them. So ideally, we like it continuously running, and they may be doing multiple tasks at a time. Another thing we had to support was draining. That's after you downscale. And I'll show you later that it wasn't a big change for us. And the final thing we had to do was feature flipping. It was a migration process. We didn't want to go 100% SQS automatically. We want to run the two things together and then kind of flip between it when we feel comfortable from our old system to ECS.
This allows us to just transfer live production traffic and live workers
correct
pretty seamlessly.
We had live traffic coming, so you want to switch between SQS and ECS. So this is a little code snippet I took. If you guys familiar, Go. But if not, I got some Ruby examples too. But this is just a little snippet to show, it's not much change for our part. The same thing was the same for Ruby. Nice thing about IAM rows, we took advantage of this opportunity and we want to clean up some stuff. So one definitely thing is we kind of tied the task with the IAMA rows. And nice thing, you kind of see the task. This is like media, and you kind of know what's the right policy should be. Like the process, the task is kind of like, it's isolated for that one work, like processing media or processing an account or rotating a video or something like that. So it's one-to-one, it's very clear. We also consolidate our IAM rows, and it definitely it was definitely a lot more cleaner. We also tightened our policy, and I like to use a little buzzword, principle of least privilege. And that's a good thing because, as I said earlier, you don't have like these process able to access other service that they're not supposed to. And that kind of also tied with the first bullet where that task, that specific process is only can access specific parts of AWS. Like you don't want our identity service to access our S3 stuff. And that's a big plus, definitely. So this was a great opportunity to kind of clean up our security policy and our IAM rows. I love this quote. Master image was deployed.
Was it today's master or yesterday's master?
I don't know. So that's the one problem we had before. Is like we didn't have a clear vision what was out in production. DevOps did not. So we've introduced this thing of like semantic versioning, and it provides tagging for our images. It ties the git tag to the image itself, and then it was a clear what code was actually in that image. Another thing is because you didn't know what was master, how do you roll back? What was the last master? And then that was another lacking thing. And we cleaned that up definitely with this semantic versioning. Last, like I said earlier, visibility, ops visibility. Ops knew what was out there running in production. They knew what was running in staging QA. Man, those guys are probably saying, thank God, whew, now I know what's running out there, right, guys? So
I'm just remembering how we used to do rollbacks, which is basically look at the Git hash and do a cherry pick back to the commit from 3 days ago, and then create it, do a new deployment there. So that is very error prone, very manual.
correct.
And now with these semantic versioning, we always know exactly what our last deploy was for each service. And if
Exactly.
you're running 40 services plus, that is even more important.
Definitely.
All right, so speaking of deployments, here's a great complicated slide. So this basically describes our deployment workflow or pipeline. So I want to run through this a little bit. We're using a few different AWS services here. This is where it gets real DevOpsy. We use GitHub, as you can see. We also use CircleCI, which is like a software as a service that runs tests and will do deploys of Docker containers. For asset management, for our repository, we were using Docker Hub, and we moved over to Artifactory recently. And then API Gateway is providing the ingress into our VPCs so that those external services like CircleCI and GitHub can talk to our internal Jenkins system. And then, of course, we have ECS. So the flow here is basically on GitHub. When we do a commit to our development branches or our staging branches, CircleCI just notices that, and it builds the container, pulls the container from GitHub, runs the test, builds an image and container, and then pushes up the image to Artifactory. And in the case of our QA or staging environment, it then goes ahead and calls ECS and actually deploys that container with no other intermediate steps. If it's production, we have one more step in there, which is basically to call our Jenkins host, and the Jenkins host is kind of the gatekeeper to deploy into production. So for that, we have CircleCI making a call to API Gateway. API Gateway assumes a role that allows it to talk to our Jenkins system internally. So CircleCI has a token that allows it to talk to API Gateway, and then API Gateway calls a Jenkins job. That allows us to have a little bit more safety when we're deploying to production. Also lets us do things like that tagging that happens in Jenkins. So when we're pulling from the latest staging build and we want to promote that to master, Jenkins automatically computes the next semantic version number, applies that, tags the container, and tags GitHub with the same semantic version. So it's pretty nice. We've got the Git tags are the same as the container tags, and that ultimately is the same as what's deployed into the task in ECS.
Auto-scaling. I want to talk about kind of like the two things we auto-scale. Like our EC2 instance, our cluster scaling, is basically just a CPU metrics. However, our task scaling is we have a couple kind of flows here. One is our workers, which I talked about earlier, that does this asynchronous stuff. They're a little different. We auto-scale by queue size, when based on the amount of stuff in the queue, if it's not consuming fast enough, we add more workers to process the queues. And also, as for our services, which is like our web services, it would be just like our EC2, kind of like CPU based. One thing that I want to note that, I don't know, I said it earlier, what ECS didn't really provide us was kind of like container draining. And that's something we kind of like had to explore on our own. I think a good way to kind of give an idea of how it works is I kind of show you a flow here. So auto-scaling, you're probably familiar. When it reaches the threshold limit, triggers our CloudWatch alarm, and then we pretty much auto-scales the ECS instance. Boom. Then all the ECS instance gets up. But at some point, the CPU is not using, is not doing as much work, and then got a downscale. There's like an event, like a life cycle event triggers that we need to downscale, and then it calls our Lambda function. That Lambda function will start signaling these EC2 containers. Okay, we need to downscale. They send that signal. And earlier I mentioned, if you recall, that I told you the only change that we need to do on our code was supporting the signal to drain. And that's the only and that's what's happening here. So you get a little high-level view. And then until the container is actually done, then it starts killing off the EC2 instance. And that's how our draining works.
So I should mention this is based on a reference architecture that I believe comes from AWS. It's available on GitHub, so that'll be on the slides. We'll share that. So the Lambda function, basically, we just used it more or less the way that we found it in the reference architecture. I don't know if this is a feature that's upcoming in ECS, but it would be nice.
Yeah, and this is something we had to implement on our own, like I said, but there's a documentation, and we'll share it at the end.
Yeah, now this is particularly important for services like workers because you don't want to interrupt them, right? When they're processing big photos, big video files. To pull that file down from S3 again would take some amount of time that would add a certain amount of latency to the work. If you're running a stateless web service, it might not matter that much. You might be able to kill off your tasks and not worry about it when the cluster is scaling in. But for our workers, we really wanted them to be able to complete at least one unit of work before getting shut down automatically. And that's basically because it's latency for our users.
Correct. And draining is because, like Zaven's saying, it's just too expensive to redo it again. And that's why we did this draining. Let's talk about, all this experience, we definitely gone through some pains and some mistakes. And I think it's best we kind of share kind of like stuff that we want you guys to avoid, which we've already experienced. So one thing, like our migration process. So as I said earlier, our migration process was, if you look at this diagram, we had two things running in parallel. We had SQS with our ECS workers and our third-party solution. And it's like Zaven said earlier, we had live traffic coming. Not only that, our code was constantly evolving. We have to get out these new features out at the same time. So that's why we had this feature flipping, And there were like two approaches we kind of did here. Like some we did feature flipping and for code that's very dynamic. But if your code is very stale, we also had teams that did just branching. So you got to weigh it out. Like, do I need, is the code stale? Branching's fine. But if it's, this is live, you don't want to be changing both branch all the time, keeping it consistent for bugs and stuff. It's a pain in the butt. It's easy rollback. Definitely easy rollback if there's problems. And tuning, that's another thing. Is the system meeting up the performance as our old system? So we were able to kind of flip between the two comparison, measure the two system, and then tune our ECS to the right level that's equivalent to our third-party solution. And last thing, we did a batch rollover. So when I mean batch, is like we didn't do a switch over all our system at one time. We switched some system maybe running the old third-party solution, or other system maybe running the ECS, SQS solution.
And migrated batches of services, right? Like media services went in one batch.
Yeah.
Identity services might go in a different batch.
Correct.
It's just a way to organize the teamwork a little bit more efficiently.
We went through the whole migration process of parallel scaling. We're also learning about scaling. Like, one thing is, don't scale way into 100% capacity, 80% capacity, because our containers take a time to launch. By the time you reach 100%, it's already too late. You're not handling the load. So 80% capacity. It's better to scale by CPU utilization, CPU reservation, not utilization. The last thing we kind of also learn is, we've always been scaling by resource, CPU, like disk space, but there's also queue size, Nobody has thought about, queues, where there's a lot of stuff in a queue, you may need to launch a lot more workers to consume these events.
So the first two bullets there are really about scaling out the cluster before the tasks need the resources. So we started out scaling on CPU utilization, which is what you would do in a typical auto-scaling group with EC2. If you do that in ECS, you might find that your tasks don't get placed because there's no more available CPU on the cluster. Cluster starts to boot up a new EC2 instance, but the tasks will fail to place until that happens. That could be several minutes or more, depending on how you're provisioning your EC2 instances.
Yeah, and it's like I said, it takes time to launch these new containers. So factor in 80% might not be right for you. You got to find the right percent. We found our by measuring, and that's how we came up with the number 80%. It's like we knew 80% by the time our next containers launch, it'll be ready.
Terraform. So a few lessons around Terraform, and this applies in general to configuration or infrastructure as code. executing your Terraform code. This requires privileges across many different AWS services when you're talking about an architecture like ours. If you want to give, say, an engineer the ability to update their stack, they might need to update everything from the task definition to the queues to the CloudWatch alarms, who knows what else, right? S3 buckets, et cetera. So although we're checking in the Terraform code with the application code, that's a good thing. We're not sure that we want to give all the developers access to do that on production all the time. So this brought up some new sort of access control problems for us that we're still kind of figuring out. We made some mistakes as DevOps, and we blew away some things in production as we were learning this. One of the things we learned is that you've got the task definition for your service described in Terraform, but then you do a bunch of deployments to that service, and so the image version is updated. So now your Terraform code is out of date, so you've got an older image in the code. So then if you go and apply that Terraform definition again, you're going to essentially roll back your service to the old version without meaning to. So we added a check, basically, in our Terraform tooling to make sure that the image that we're pushing out is actually the latest image that's in the repository. And then finally, we decoupled unrelated Terraform modules. So if I'm going in to make a change to an SQS queue, I don't want to need to check all of the code for the service or the cluster, make sure that I'm all up to date. I just want to make that one change. Terraform, of course, provides some rails to prevent this kind of thing, but they're not foolproof. And you have to inspect a big list of changes on your screen. So there's a lot of human error there. So moving on, the last section is about our benefits that we realized. So cost savings. This is one of the best benefits that we've gotten from moving to ECS. This is just an example of some of Lawrence's media workers from the old system. So you can see there, this is 3 different environments, QA, staging, and prod. And to maintain some sort of high availability in our old way of doing things, we needed at least 2 EC2 instances per environment, so we're spread across 2 availability zones. In production, we're usually running 3 or more. So even if the service is not running under full load, we're using, in this example, 9 EC2 instances to run this one microservice. If you don't have a lot of time to optimize your services, do a lot of benchmarking, and find just the right instance type, that means you're going to be over-provisioning your compute. And I think AWS makes a lot of money on this kind of thing. So they love it. You might not. So we were trading efficiency for HA in the old model. So now to contrast this with an example of an ECS cluster, this is one of our QA clusters. You can see down here, we're running 50 services on this one cluster. We're using 9 instances. So same number of instances, we're running 50 services. Now, admittedly, the CPU utilization, the overall resource utilization on this cluster is very low. It's our QA cluster. But still, it's like a factor of 10 better if we're looking at 3 different environments. So you can imagine spread across production with full load of users and all of that, it really adds up a lot. We think we're going to save like 75% of our EC2 costs by moving to ECS. This is just an example of our cluster utilization. CPU reservation is on the left here. So that shows that we're reserving all the tasks, or all the services running on this cluster are together reserving something around 80% of the total capacity on the cluster. It's nice to be able to measure that. It's nice that we know how much capacity we have to grow into. And on the right, our utilization, again, is quite low. So to me, that just says we've got some work to do still, and we can do even better with cost efficiency. A little bit about metrics and monitoring in ECS. Things the team like about it, benchmarking each service's resource requirements is quite easy, like I mentioned. And we also like the ECS event stream. That's really helpful for monitoring the sort of task placement errors and that kind of thing that you'll see in real-life operations on the cluster. And then on the negative side, there's a lack of container-level monitoring with CloudWatch and ECS. It's not easy to tell at a glance all the containers that are running on a host. So we've actually started using Datadog, which we like a lot for container-level monitoring. And then finally, the basic CloudWatch metrics only come in at 5-minute intervals. That seems pretty quick, but when you're talking about scaling of workers that are processing media on people's phones and desktops, you need to be able to be kind of up to date. We want to know what's going on at a more granular level. And I guess to get that, you pay more with enhanced metrics.
Well, I hope that was all useful for you guys. We've pretty much covered, like how GoPro's platform is based on the ECS, and then we kind of explain like why we chose it, and kind of show our migration process and some of our pains, and we go. And we definitely realize, big cost saving, better deploying, better orchestration, stability. He's happy. I'm happy. You guys could also be happy too. Maybe you should try it. Other than that, get a GoPro or a Hero phone. Thank you, guys.